Okay, everyone, good morning for yet another lecture for numerical methods. We are going to continue now with interpolation. Last time we finished off with linear interpolation, where we connected 2 points with a straight line. And then we applied that to a large data set that had many points. And it ended up connecting every 2 points, connecting them with a straight line. And then we were able to ask that interpolant to find the value at some intermediate point between all of those points that were given to us, right? Today, we're going to ask the question, okay, can we do better than that? Clearly, a linear interpolation is just connecting 2 points, is taking 2 data points and providing information. Can we use more data points? And that's the question that we're going to ask today, okay? And let me just this right here. All right, so last time we said with 2 points, we could, given 2 points, x1 and x1, y1, x2, y2, we could fit a straight line of the form a0 plus a1x. Now I changed the coefficients for a reason. Last time I called them mx plus b. Today I'm going to call them a0, a1, and so on and so forth. And notice that the subscript of the coefficient corresponds to the power of the x value. So a0 is like multiplied by x to the power 0. Okay, a1 is multiplied by x to the power 1. And then we're going to expect a2 to be multiplied by x to the power 2, as you'll see next. Anyway, staying with the linear interpolation, we were able to fit this straight line by applying the straight line model equation, a0 plus a1x, to both points. We said y1 is a0 plus a1x1 and y2 is a0 plus a1x2. And then we were able to form a linear system of equations. Some of you solved it by hand, computed the slope, etc., and that's completely fine. Okay, but I also I stressed last time that you should think of this as a linear system of equations for the reasons that we're going to discuss today. And then you're able to solve for a0 and a1 together from the linear system. Now, we're gonna take this one step further. Like I said, with the straight line, we're using only 2 points. So we're only using 2 pieces of information from the entire data set. What if we use 3 pieces of information, 3 data points? For that, I claim that with 3 data points given here by x1, y1, x2, y2, and x3, y3, we are able to fit a quadratic, like a little curve, okay? That's a second order polynomial. And the form of this polynomial is y of x is equal a0 plus a1x plus a2x squared. Now you see the pattern of the subscripts. All right, now, first thing you ask yourself, what are the unknowns in this equation? It's the coefficients. It's not the x values, because the x values are going to be input values provided by the user and the data specifically. So now my question to you is going to be the next class activity, is find the system of equations that will solve for the that we have to solve to find the coefficients a0, a1, and a2. Okay. And just like last time, we're going to switch back to Zoom and do the discussion. But once we switch back to Zoom, please mute your YouTube video. Okay, and then you can unmute your Zoom once we are back on Zoom. Okay. Okay. So now I am back on Zoom, and I'm also streaming on YouTube. Now, in a few seconds, glance on your YouTube screen and see the setup. You're going to see me, and you're going to see a bunch of you, and Jennifer is smiling. Looks like it's working. Yeah, is it working for you? Okay, now don't listen to YouTube. Later, when you review the video, that's what you're going to see on YouTube. But right now, in real life, we are talking to each other over here, okay? And you still have about a minute, okay? And if you want to remember the question, now glance on YouTube. I have that slide with the question on it on the YouTube video. But please mute your YouTube, okay? So that you don't hear me both ways. Okay, give you about a minute. I just want you to write down the system of equations, okay? To solve for A0, A1, and A2. Remember what we did with the straight line. We just applied the model. Think of the polynomial fit as a model equation that you want to apply to the data points that you're given. So simply you got to apply it to point 1, point 2, and point 3, and then see what you get, okay? And then collect that into a system of linear equations. All right, I'm gonna call time. Let's see, do we have any volunteers today? If you volunteered, next time do not volunteer. Let's, I wanna see some new faces volunteer, please. All right. Megan, are you with us? Okay, let's try Quaid. Quaid? Okay, not with us. All right. Corwin? Yeah. Do you have like any thoughts on how we can figure this out? Okay. So just would you mind just saying the first equation, what you did there, and what the first equation is? Mm-hmm. 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 Got it. That's right. Notice the x1 squared. Now you have like these two indices. And the second equation looks the same. Who wants to give me the second equation? Sophie? Yeah. Mm-hmm. Okay, so what is changing in that equation? So there are the coefficients in red, right? That those will be the same for all the points. What is changing in the equation? It's the x values, right? Yeah. So try again. Yeah. So A1 x2, I think you meant. Yeah, yeah. A1 x2. Remember, don't mix up the indices. Think of different quantities. Let's say we had called these coefficients A, B, C, right? It would be A plus B x2 plus C x2 squared, correct? Now equation 3 follows. So what Soviet and Corwin did, they simply applied the polynomial, the quadratic equation to these 3 points. And for those 3 points, you're only given x and y values, right? So y1 is going to be a function of x1, y2 a function of x2, y3 function of x3. Then were you able to convert this into a matrix? I want the system of equations. Let's see who's got that. I'm trying to pick some new folks. Joshua. Okay, not with us. All right. Let's see. Harris. Yeah, do you have the system of equations in matrix vector form? All right. Do you need any help with that? Do you at least have the governing equations? Okay. So now, yeah, it's just a matter of converting those to matrix vector form. Okay, so I need a volunteer now who's got the answer. Yeah, that's right. Yep. Times. Mm-hmm. 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 Excellent. Thank you, James. All right, so I'm going to have to switch back to the slides to explain what James did. Now we're going to switch back to the live stream where I'll show you the answer. Okay, so please go ahead and mute your Zoom audio, and then we will be on the YouTube live stream. Okay, so that discussion went really great. Your colleagues figured it out. We figured it out together. What we did, we applied the quadratic equation with these red coefficients to the points that are given to us. Okay, so we had to apply it 3 times. When we apply that 3 times, you end up with 3 equations and 3 unknowns. Now ask yourself always, what is given to us and what are the unknowns? Over here, the unknowns are, show them specifically in red to help you. They're the coefficients of the polynomial. Remember, we want a polynomial that's a function of x. We can apply the whatever x we want between the data points that we're given to give us a y value, okay? And so with that, what we did, we have the 3 points. We apply the model equation. Point 1 is a0 a1 x1 plus a2 x2 squared, and then y2 and then y3. We get the same thing. The only thing that's changing are the y and the x values, but the coefficients remain the same. Okay, those are the unknowns. We're trying to find those. So now next, we convert this simply into a system of linear equations. What's a system of linear equations again? What's a matrix form, matrix vector form? They're the same as a system of linear equations, right? And with the ordering that we are given over here, the matrix vector multiplication over here should reproduce that system of equations. So if you do this vector matrix multiplication, what are you going to get? You get 1 times a0 plus x1 times a1 plus x1 squared times a2, which is going to be the first equation over there, okay, equal to y0, all right? So, and that's how you do that. Okay, so now we're going to generalize this because obviously, what if you had more data points, a lot more data points? What if you had 100 data points, right? Or, could you fit a polynomial of, with these 100 points? Clearly, you would think that the more data you have, the better accuracy you're going to have with the polynomial. So let's see what happens. With 2 points, you can fit a straight line, we said. With 3 points, you can fit a quadratic. So that's an equation of, that's a polynomial of order 2. With 4 points, you can fit a cubic, right? So why is that? What are we looking for? So 4 points, cubic, we're searching for the 4 unknown coefficients. Remember, a polynomial always have this constant that is added to it, okay? So that's why with 4 points, you can fit a cubic. With n plus 1 points in general, you can fit an nth order polynomial, okay? And to do that, so I've written the polynomial now. Assume you are given n plus 1 points. I'm going to move my mouse out of here. And I'm showing here the unknowns in red. So you have these coefficients that you're looking for, a0, a1, a2, and so on and so forth. They are the unknowns. there are n+1 unknowns, right? And those n+1 unknowns are going to fit into the n+1 data points. So remember, don't confuse the nth order polynomial with n+1 points. Each point is going to give you an equation. Think of it this way. And your polynomial, how many unknowns does it have? n+1, then you need n+1 equations, okay? So we have n+1 unknowns, we need n+1 equations, so we need n+1 points, one equation per point. So keep it as a rule of thumb. For an n+1 data points, we can fit a polynomial of order n. So if I give you 10 points, you can fit a polynomial of order 9, okay? And if I give you 15 points, you can fit a polynomial of order 14. Now, whether that makes sense or not, we're going to talk about that in a minute. Now, remember, there's a critical piece of information over here. An interpolating polynomial, by definition, must go through each and every point of the data set that you used to build it. So if you took 10 points of, let's say you have a very large data set and you said, I'm going to pick these 10 points and build a 9th order polynomial, some subset of 10 points. So that polynomial, by definition, is going to have to pass through those points. Why? Because that's how we built it. We said this polynomial should pass through point 1, should pass through point 2, should pass through point 3, and so on and so forth. So the output polynomial should pass through those points. That's a critical distinction from what we're going to learn after, which is what we call regression. Okay, so in general, given n+1 data points, you get this system of equations, which is a generalization of the straight line and the quadratic that we did, right? So with the straight line, we had only one, an x1, x2, and we had a0, a1, and we had y1 and y2. And then with the quadratic, we had 3 of those. And then for an arbitrary nth order polynomial, we had something like this. Now, be very careful. You could construct your own polynomial. You could say, I want a polynomial of the form a0, or let's say a plus bx squared plus cx to the 5th. You should be able to apply this strategy to do the same thing. For these polynomials, we're assuming that the coefficients are all non-zero, okay? But you can fit any kind of polynomial form that you like, okay? You should be able to derive that. And by the way, this is a classic exam question. Is give you a polynomial with a strange form and ask you to come up with the system of equations. Don't memorize the matrix and blindly spit it out. Do the derivation again, okay? Now, the operation is simple now. In our attempt to find the coefficients of the polynomial, we obtain these coefficients by solving this set of linear equations, okay? It looks like I can do this here. You don't have to point this way. I can point into the slides, which is easier, and evaluate the value. Once you get the coefficients, that's it. Now you have the formula as a function of x, and then you can get the approximated or interpolated value using that, okay? Now we're going to do this in Python, okay? We're not going to do this by hand. I will ask you to just develop the system of equations as needed, but for all practical purposes, it gets too complicated solving these large systems of equations. So we're just going to use Python. And there's a nice function in Python. There are 2 functions in Python. One of them is Polyfit, and the other one is Polyval. And we're going to use both of those to do generalized polynomial fitting. So we're going to start with the Polyfit function. And I'm showing you here, you can't see my finger, but I'm showing you here the usage, how we use this. We first declare P. I'll define what P is in a second. We call Polyfit, and just like Interp, Polyfit is going to take an xi and an yi vector. Those are the input independent variables and the input dependent variables. Those are vectors. That's your data set. Now, there's an additional item, there is an additional argument in Polyfit called degree, or deg, D-E-G. That's the degree of the polynomial, okay? Now, you have to make sure, and that's a user-specified value, okay? You have to make sure that this degree, if you are given n+1 points, degree is n, okay, to get a polynomial fit. If you choose any value other than n, you're going to get something else called regression. We'll talk about that later. But for now, for this chapter, degree must always be, if you're given n plus 1 points, you put n for degree. So if you had your data set had 19 points, then degree would be 18. And you can easily do this. We'll show you. Take the length of the array xi, and you do length minus 1 to give you that degree. Okay. Now, P, the return value of Polyfit, is simply the collection of coefficients. That's the solution. Those are the coefficients of that polynomial that you just built with those data, with the data set that you provided to Polyfit. And that's just simply an array of coefficients. And it starts by the last coefficient, okay, all the way to A naught. So it starts with an minus 1, and so on. We rarely probe that. You know, you might be interested in looking at it, let's say, and you want to compare it to your own solution of the linear system to see if you did it correctly. But we rarely look at that. However, P is the collection of coefficients. Now, once you build that polyfit, essentially you've built a representation of a polynomial. You clearly now need to define the polynomial because all you have now is the coefficients. So you can do this the brute force way and define a function and loop over those coefficients and multiply them by x, etc. Or instead, you could use this really neat function called Polyval, polynomial evaluation. And Polyval takes two arguments. It takes a vector of coefficients for a polynomial. It assumes you're giving it the coefficients of a polynomial, and it evaluates it at a value that you give it, or an array of values that you give it, xe. And it's going to return ye, just like we did last time. Okay. So next, we are going to do our coding activity. We're going to take the Jupyter notebook that we were working with last time. We did linear interpolation and we did inverse interpolation. The next section is going to be on polynomial interpolation. And I'm going to now see you on Zoom. Please do not forget to mute your YouTube stream. Okay. All right, everyone. I assume you're finishing off with the live stream and coming back to Zoom. We are going to now switch to our coding activity. Okay. And let me find that. So get into the Interp activity 1, please. Interp activity 1 that we were working on in class last time. And I'm going to go ahead and share my screen with you. Okay. Excuse me. Okay, can you see my screen now? We're all on Zoom now. Okay. Hope you can all hear me. Okay. So we left off last time with this data set. You probably want to execute that data set again. So I'm going to execute that first cell and then the second cell to get row and t and import numpy and interp, etc. So now we're going to the section of polynomial interpolation. Okay. Excuse me, all the way down here. Now from numpy, like I said, we're going to import Polyfit and Polyval. Now remember, over here you are given t and row, and t is the independent variable and the density is the dependent variable in this case. Okay, so you execute this cell. Now we're going to ask Polyfit to build a polynomial interpolant. Now remember, the format for Polyfit was xi, yi, and degree. So what are we going to put here? Take a moment and let's see what we're gonna put here. So again, it takes independent variable input, dependent variable input, and a degree. All right. Do I have any takers, please? Let's see, William. Not here. Mitchell. I'm just randomly picking people. Yeah. Yeah, that's the independent variable, right? So those are, yeah, the xi values. And then this, correct. Okay, now what about degree? Okay, so who's got an answer for degree? Correct. Yes. So simply, we're going to take the size of the entire data set. Okay, we're going to take the size of the entire data set, and we are going to subtract 1 from it, right? So we're going to do len. Oops, you could do t or row, it doesn't matter. So len of t minus 1. Okay, go ahead and execute that. And when you execute that, it's going to throw an error. Forget about this error. We're going to discuss this shortly. Okay, so what is stored in coefficients? I just explained that in class. If you print the coefs, it's going to be an array of coefficients starting with an, the last coefficient, all the way to a naught. Now, how many points do we have in the data set? We have, let's say, len t is 19 points. So this is a polynomial of order 18. Okay, so that's got x to the power 18 in it. Okay, it's a huge polynomial, all right? So now I'm asking you, evaluate the density using Polyval at 412 and 450. Okay, what do we got here? Yes, yes, go ahead. Mm-hmm. No, you are misunderstanding the purpose of doing linear space last time. The purpose of doing linear space is we created arbitrary points to evaluate the interpolant at. Those points cannot be used to create a new interpolant because they're not going to improve the quality of the data you're given. Does that make sense? The quality of the data you're given are those 19 points of temperature and density that were given to you from the table. All we did with the lens space was an illustration. If you had arbitrary points and you wanted to evaluate the interpolant at, that's all. But they're not going to improve the data. Notice the interpolants, as I'm showing here, those data points, they all fit on the straight line, because what defines the straight line are those two black data points, okay? So we cannot use this to form a higher order interpolant. It just will not make sense at all, okay? Does this answer your question? Okay. All right, so now let's stay here, please, at Polyval. So we were gonna call Polyval. We just calculated the coefficients. So let's see, who's gonna help me with this? Go ahead. Who's talking? Oh, Carl. Okay, so I'm gonna switch to speaker view. Go ahead, Carl. Coefs, correct, because Polyval, yep, in the first argument, it takes the coefficients of a polynomial. Okay, and the second one, correct. 412 and 415. Okay. Okay, and you press Shift Enter, and you get 0.847 and 0.8412. Those are the densities, and we can double check. So we said at 412 and 415. So that's around over here. Kind of makes sense, right? It's not completely out of the ordinary, correct? Okay. Okay, so now I'm going to ask you to go ahead and do it at 980. All of you. Just type in, Polyval, just like Carl was telling us, coefs, and what do you put here? 980. Okay. What did you get? Sammy has a grin on his face. Yeah. Yeah. Okay. Anyone else has any comment on that? Yeah, you got, did you all get a negative value? Yeah. That doesn't make sense, correct? Doesn't make sense. So let's see what's happening. I really love plotting things. Okay, I really love plotting things. So now we're gonna take that polynomial and plot it. Okay, we're gonna plot that polynomial, okay, on top of those data points. Now, by definition, that polynomial is gonna go through those data points by definition. So if we plot it on the data points, it's just gonna go through them, no issue. But what I wanna do, I wanna plot it in between the data points. So that's why I need to create this lint space. So I'm going to create I'm going to recreate this lint space. Okay, and I'm going to try to plot the polynomial. Okay, so here's what we do. We do another lint space. You can copy and paste from what we did before. Just create a bunch of points for the temperature from 100 to 1000. Those are the bounds of our data set. And I want to put 100 points. So that is going to force the polynomial to evaluate itself in between the data points, okay, that were given to us, right? And then I'm gonna evaluate those points with Polyval now. Polyval, we're gonna evaluate the coefficients all at those xe, okay? Next, we're gonna plot the original t and rho over here. I'm just gonna put them KO as black dots. And then I'm gonna do the polynomial. I'm gonna do it in red, but I'm gonna make it connected with straight lines. Okay. So go ahead. I'll wait for you to type this up and print and execute. Show me what you get, or see what you get. Abby. Diffs. Yeah. Yeah. Did you all get that? All right. So this is what you get. It not only dips, it also overshoots a little bit over here and then goes down over here. And that is a negative density. So if you do a grid, t.grid, okay, right? So this is 0 and you get into a negative density. And why do you think that's happening? Can you repeat that? I didn't hear you. But you are not, yeah, it's not correct. That will not be a polyfit, it will be a regression. But that still doesn't explain what we're seeing, right? Okay, so it's a little bit, I didn't expect you to know the answer, but it has to do with the fact that high order polynomials, okay, can be oscillatory. Now notice this polynomial is anchored at the data points that are given to us, okay? And that's by definition, by construction, it is going to pass through each and every data point. Those are the black dots, okay? But in between, it can do whatever it wants. It can go up and down, up and down, up and down as many times as it wants, okay? Because the higher the degree of the polynomial, you're going to get more oscillations because you need to have roots for the polynomial, right? It needs to cross the 0 axis. And also think about it. You have x to the power 18th. Now imagine taking the power of a very small or a very large number, taking it to the power 18th. That's going to create significant round-off errors, even in the calculation. And so it leads to significant numerical errors as well. The bottom line, the message that we're going to send about polynomials is going to be, they are a bad idea. Any polynomial that is higher than order 2 or 3 is probably going to be a bad idea for your data. And now I'm going to switch back to the lecture to tell you a little bit about that and what we can do about it, and then talk about a fix for it. Okay? I'm going to stop my share. Yes, go ahead. You are, and you just said what I was going to say. I want you to build on that because you say it better than I say it. So go ahead, continue what you're saying. But 2 points is going to give you a straight line. Maybe you mean 3 points. 3 points, and you fit. So you take every 3 points, yeah, and fit a quadratic, right? Okay, so that's exactly right. So what Abby is saying, look, you just said that high order polynomials are a pain. And one way to avoid that is to stick with low order polynomials. However, we can't fit a second degree polynomial to 50 points or 100 points. So why not take any 3 points at a time and apply the interpolation there? And this is exactly one of the solutions to this problem. However, it is extremely complicated to do this with Python when you take, or with any programming, because you're gonna, which 3 points do you take? If you wanna fit the entire, if you are interpolating at one specific temperature, you find the 3 points around it, you do a quadratic, and you're done. But if you want a general representation of the data, right, for the entire data set, it's going to be very complicated to try to find which 3 points you take. You take point 1, 2, 3, and then 2, 3, 4, or 3, 4, 5, or 2, 4, 5, right? So that evaluation becomes annoying for a general data set. The best thing you could do is search in the data set, find the 3 points that are closest to your value that you want to interpolate to, whether on the left side of that point or the right side of that point, fit a quadratic, and then you're good. And that's a completely legitimate way of doing it. But I'm going to share with you today an even nicer way of doing all of this so that you don't have to worry about searching for the data points. So to do this, Abby, you're going to have to implement your own Python algorithm to find the points that straddle your point of interest. Okay? All right. Great critical thinking. Okay, so I'm going to switch back now to the other side of the internet on the live stream. Please mute yourselves on Zoom, and I will see you over there. Okay? Okay. We saw in the coding activity that polynomials can be oscillatory, and that's problematic. Okay? And that's quite a problem. And what we want to avoid high order polynomials. That's going to be a problem with any high order polynomial. Now, what one of your colleagues suggested is that why don't we take any three or four points at a time and apply an interpolant to those points? And that's a completely legitimate solution. You're going to have to do this, though. You're going to have to create your own routine and probe a data set and say, I want to find the 3 points that surround a given value at which I want to interpolate, and then use that algorithm to process any data that you want. Okay, Python, unfortunately, is not going to do that for you. It doesn't have a mechanism to do that for you. Unlike linear interpolation, where with linear interpolation, we asked Python to just fit straight lines between every 2 points, right? And that was a well-defined problem, okay? Now, like I said, this is unfortunately cannot be done in Python. However, there is another way and an alternative to full polynomial interpolation of a data set, and that's called splines or spline interpolation that we are going to discuss next. The idea of cubic spline interpolation, they're called also cubic splines, is that you take every pair of points in the polynomial and fit a cubic polynomial to those points. So in the example I'm giving here, we have 4 data points, and for each 2 data points, I'm going to fit a cubic. You ask yourself, how can you fit a cubic? It's got 4 unknown coefficients to 2 data points, where we're going to hook them all together so that we get enough conditions, okay, that we get enough conditions to find all of those coefficients. And it turns out this is a brilliant solution, brilliant fix to this problem. So for n plus 1 points, okay, we want to find n splines. So take this case that we just did over here. We have these four data points, and we can fit 1, 2, let's see, the one in pink, the one in green, and the one in blue. We can fit 3 splines. So in general, you have n plus 1 data points, you can fit n splines. Now, for each spline, you have 4 unknowns. Why? Because the spline, by definition, is a cubic polynomial. And a cubic polynomial is of the form, it's got 4 unknown coefficients. So A0, A1, A2, A3, or in this case, A1, B1, C1, and D1, and AB is A, B, C, D, right? For each one of those, okay? So we have 3 splines over here. So in total, you have 4 times n unknowns. So therefore, you need 4 times n equations or constraints to be able to solve for all of those unknowns. And that's pretty simple. At the interior points, what you do, you have, in this particular case, you have 4 conditions that you can satisfy. This blue spline needs to be equal to the data that's given. Remember, a spline, like a polynomial interpolant, must go through each and every data point. So the blue spline at x2, y2 is equal, the blue spline at x2 is equal to y2, the green spline at x2 is equal to y2. So that gives you 2 conditions. The green spline at x3 is equal to y3, the pink spline at x3 is equal to y3, gives you another 2 conditions. In general, for all interior points, from that condition, you get 2 times n minus 1 constraints by applying that. Then at each point in the interior, the first derivatives need to be equal. So in other words, first derivative of blue spline at x1 needs to be equal to the first derivative of the green spline at x1. Same thing for the green and pink spline at x2. So that gives you n minus 1 constraints. Same thing then for the second derivative. We want to match, make it nice and smooth, okay? The method that Abby was talking about, where we could apply interpolants locally to each and every 3 points, you might not be able to satisfy a smooth interpolant. You might get kind of different quadratics that are not nicely connected through the first and second derivatives, okay? So this will make sure that this is fixed. And then the first and last points, they need to pass, first and last splines, they need to pass through the first and last points. And finally, the curvature at the first and last points must be specified, typically by the user, okay? So I'll explain that to you in a second. What we do here is simply say that the second derivative is 0. So that's what's called a natural spline. You can specify it. If you have other information, you can specify another value, but in general, that's the default that goes into Python. And we're going to use Python to do that. So here's a breakdown of how we apply these conditions very simply. Like I said, I switched the colors a little bit. So the spline at x1, so f1 at x1 is equal to y1, f1 at x2 equal y2, and then f2 at x2 equal y2, f2 at x3 equal y3, and so on and so forth. And then the derivatives at the points that are in the interior points, the x2 over here, x2, y2, and then the x3, y3 over here. Those derivatives, they should match between the green and red and the pink. And then same thing for the second derivatives, okay? The second derivatives over here. And then finally, the derivatives, the second derivatives at the endpoints, they also need to be specified. We specify them as 0. Anyway, long story about splines. You're not going to be asked to derive splines, but you need to understand the conditions that are used to derive these splines. So now you have all of the conditions necessary. Think of this. We have 3 splines over here. Each spline has 4 unknowns. So we got 3 times 4 unknowns. That's 12 unknowns. So we need 12 equations. You can count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are 12 equations. You apply the equations, you get a system of equations, okay? And you solve that system of equations and you get the coefficients, and then you plug that in, and then you get your cubic spline interpolant, okay? The advantages, it provides a really nice and smooth interpolant. It's more accurate than linear interpolation, and it looks really nice, better than polynomial interpolation, and doesn't get this oscillatory behavior that you get from very high order interpolants. Just requires a little bit more work to do, however. That's the primary disadvantage. But because we're not implementing that, we don't care. We just want to use the built-in spline interpolant. Splines are some of the best interpolants you could use to interpolate data, get nice and smooth. So now on to Python. How do you do this in Python? Again, Python provides a library that provides a spline interface for us, but that's not going to be through NumPy. It is going to be through SciPy. So from SciPy.interpolate, we import the module or the function called cubic spline. Actually, the module is SciPy.interpolate. It has a function called cubic spline, which builds splines. And then what I'm showing here is the first line is CS equal cubic spline XI, YI. Again, the interface remains the same. You have input independent data, input dependent data. CS equal cubic spline of those data gives you the coefficients of the spline, okay? That's just the coefficients and the system to build spline interpolants, okay? Now remember those, with the spline, you got to find out where you are between the data points and apply the correct spline. So it's a little bit more complicated than just coefficients of the spline, this CS. But the great thing about it, to do an interpolation using a cubic spline, the cubic spline that you just built, you just call this CS, which is like a functor, on the value that you want to interpolate, XE over here. So YE equals CS of XE, that gives you the interpolated value using splines at the point XE, or the array of points XE, okay? Now we're going to continue our coding activity, and we're going to do the last activity with splines, with that interpolant notebook, okay? I will see you on Zoom. Okay, so now I'm seeing you on Zoom, and someone is playing radio or something. Now, okay, I'm on Zoom. You can hear me. Someone is playing some radio. This is going to show up on YouTube, and now YouTube is obsessed with copyright infringement. Remember that video that I put early on about hidden figures? It slapped me with a copyright infringement thing, and I told them this is, fair use for education. So they said, okay. So every year, the same thing happens with that video. So I'm hoping whatever radio program was showing is not gonna get me an infringement, but anyway, silly things like that. All right, so cubic splines. Let me share the window with you. Okay, I'm gonna share my Interp activity over here. Okay. Can you see me? Can you see the window? Okay, great. All right, so from scipy.interpolate, import cubic spline, right? And then we're gonna call cubic spline on the input data. All right, I need an answer. Yep, row. You're right, thank you. Okay, and then we build our CS and now simply evaluate the density at T 412 and 415. We're gonna do CS at 412 and 415, 412 and 415. And then it gives you two values. They look okay, that's great. Now the question is, let's see if we can do it at 980. Again, CS at 980. It gave me a reasonable value. Best thing to do now is go ahead and plot that entire cubic spline, but we need a lot of points to plot it at, right? So that's why we created this lin space. We're not creating new information. This lin space is just a convenient thing, to allow us to essentially see how the fit or the polynomial or the cubic spline fit looks like. So what I did here is create a new lin space. I call it XE. Let me call it XE. And then YE is CS of XE. And then I'm going to plot XE and YE. And when you plot that, you get this really nice and beautiful and smooth curve. Now remember, by definition, by construction, all of those polynomial interpolants, splines, polynomial, linear, quadratic, all of them, by definition, they pass through each and every point of the data set that was used to build them. Okay? Anyone not getting this? Not getting what you're seeing here on the screen with the code? Okay. This should be a template for you to use in the homework. There's really nothing fancy going on over here. Yes, someone has a question? Braden. So yes, but I need to step back because I think there's something you misunderstood here. What Excel or those other tools are doing, they're doing regression. They're not doing a fit or an interpolation. Regression is something different. We're going to learn about that next, okay? And we will be able to get that equation. Now over here, to get that equation, all you need to do to get is the coefficients, right? So Python is not going to spit out that equation to you, but it'll spit out the coefficients. So for the polynomial case, okay, all you have to do is print the coefs like we did here. So this would be your equation would be, and you can parse that and print it out if you want. Your equation would be 5.8 times 10 to the minus 46 x to the power 18 minus 4.8 times 10 to the power minus 42 x to the power 17, and so on. That's your equations. Those are the coefficients, okay? And for the cubic spline, I would have to look at what the CS contains. So I think this contains, so we got to look at the output. Yeah, it's a little bit complicated. So the CS contains the coefficients of the spline that corresponds to each and every pair of points, right? And so you don't have a single equation here, Braden, if that makes sense to you. Each one of those curves is a different equation. So in total, you have 18 equations over here. You don't have a single equation. What you're talking about is something different. You're talking about regression, polynomial regression, which we will learn about next, where you can fit one curve. When I say fit, you can fit one curve and you get an error with the data. So what is the error with the data over here? Zero, exactly zero. Yeah, because we pass through each and every point, okay? So we can recover those data exactly, because by definition, that's how we construct those. What you are referring to is regression is not going to necessarily pass through each and every point, okay? So please don't confuse the two, okay? This is interpolation. It's very different than regression, okay? Regression, we will learn. It's actually my favorite part, my favorite chapter of this course. But regression will essentially develop a model for you for the data, a model for the data, okay? A trend for the data. This is not trend. This is exactly passing through each and every point. Okay, so I hope this helps. Okay. All right. So now I'm going to switch back to the other side of the internet, and please mute your Zoom. Excuse me, and we will finish off with this chapter in this course. All right. So now that we looked at how we can use cubic splines and how powerful they are, we're gonna now extend our interpolation into multiple dimensions. We're gonna go to 2 dimensions. You can go to 3D and higher dimensions. Gets really complicated and annoying, the algebra. But I wanted to give you a flavor of how you can apply linear interpolation to higher dimensional data. Okay. Assume now that you have 2-dimensional data. For example, now you have the specific volume of water at various temperatures or pressures. Another example we will do is that you have a heat distribution with X and Y on a plate, for example. So our independent variables now are pressure and temperature, shown here in the first column over there, the first column over there. I'm always messing up my directions because I flipped my camera so that I have the impression of always looking at you. Anyway, so the first column is the pressure, and the first row in the table, okay, is the temperature. So think of these as your X and Y independent variables, and then you're looking at the quantity called specific volume, which is given in this table over here, okay, in this table. Now, suppose you want to find the specific volume of water at those 2 points, at 0.75 bars for the pressure, 0.75 bar, and 175 Celsius, okay? So what do? You got these 4 points over there surrounding it. You want to do some form of interpolation, okay? And the idea is simple, is that you apply 2 one-dimensional linear interpolations and try to get the value in between, okay? So the idea is simple. When you have, and this only works for structured data that is kind of nicely and structurally spaced, not just arbitrarily put together. So nice tabulated data like that. So you interpolate in one direction, you interpolate in the second direction, and then essentially combine the values. And I'll show you how you do that. So in this case, we have, I'm gonna call my independent variables as X and Y, okay, for simplicity. Forget, I know previously we were doing Y equal function of X. Now we have X and Y as independent input data, think of those, and phi is our dependent variable. So in other words, for this example, phi is the specific volume, and it's a function of temperature and pressure, which are our X and Y values. And this is a generic plot that I'm putting here, Y-axis and the X-axis. and I'm putting the values of known quantities, in this case, the specific volume. I'm going to call those phi11, which is the value of phi, or the dependent variable at x1 and y1, and then phi21 at x2 and y1, and phi12 at x1, y2, and phi22 and x2, y2. So you can parse those given specific data that you have. Now, our purpose is to find some value, the value of phi at some arbitrary xy in between those 4 data points. Remember, interpolation is going to only work well within the bounds of the data that you give it. Okay, so the bounds of the data here are visually kind of clear between going from phi11, this kind of small square or rectangle, phi11 to phi22, and we want to find the dependent, interpolate the dependent variable in between those points. So one strategy would be, we first interpolate in the y direction. So we take, just like we did with standard linear interpolation. So we fix x1, so x1 is fixed, and we just do linear interpolation between phi11 and phi12. It gives us this yellow dot over here, this yellow dot. And then we do another linear interpolation between phi21 and phi22. So you get these 2 yellow values. And now with those 2 yellow values, you can do one more interpolation. Let me see my hands. And then you get phi. Okay? And you can develop an analytical formula for that. You can switch the order. You can first interpolate. You fix y and interpolate in x. Same thing. And then interpolate in y. Both of those will give you the same answer, and that answer is given in this very complex formula. Okay, this was deriving this formula with some guidelines and some slight changes to help you with the algebra. This was one of the exam problems, a bonus exam problem that I used to give. So you might be interested in working through this if you're curious. Okay. But for our purposes, you should be able, however, to describe how this process works. Okay, say we can interpolate in one direction, interpolate in the other direction, or interpolate the first 2 points, second 2 points, and then interpolate the result. You should be able to describe that, okay? But in practice, we do this in Python. I'm not going to ask you to do this in Python right now, and not in the homework, although it's worthy if you want to play around with it. So in this case, we use a function. So I'm showing you this as more of a, like what's next? What is the next step? Where do we take this next? So in Python, there's a function called Interp2D as opposed to Interp, and it comes from SciPy, not from NumPy, interestingly. So these kind of more complex interpolants, they come from the SciPy library, just like the splines. And the Interp2D takes xi. Now you need 2 independent variables. We call them xi, yi, and a dependent variable, which is zi, so xy, z, that's the surface. And you have to specify a method. So if you look at the interface of Interp2D, it takes xi, yi, and zi, and the method. What we just explained to you is, linear interpolation. But you can do higher order cubic and quintic, and gets really complicated. It will do the things behind the scenes for you. But to reproduce, if you want to verify something you did by hand, I would use linear for the method. And I described these quantities here in this box. You got xi, this vector of independent variable 1, yi independent variable 2, zi the dependent variable, and that should be a 2-dimensional vector, right? Because those are the entries in the table, and they need to correspond to the xi, yi. So put them in the same order, okay, that the data was given to you. The method, like I said, you could specify one of 3 methods in Python. Now the return, now to use this, so this Interp2D is gonna build the coefficients, whatever, is gonna build some complex data structure to be able to apply interpolation for any points in between the data that you've given it. Okay, so to apply that, you use, now see how I did this? I called this F2D equal Interp2D. That's like the CS for the cubic splines. And I kind of stand over here between these 2 boxes. Okay, so F2D is like a functor that you call upon to evaluate at certain values. Now, because this is 2D data, this F2D is going to take two arguments, an X and a Y value, or two new independent variables, and it's going to return a single value, right? That's going to be ZE that I call here. Now, this is a specific example. Feel free to just copy and paste that in Python and play around with it and see what happens. I'm taking heat transfer data of temperature data in a heated plate. And that plate is shown over here in this little box. Let me stand next to it. Okay, it's kind of hard to, I don't know how the weather people do it. So there's this little box over here. Okay, so you see the data is kind of very sparsely distributed. Okay, but those data were measured, let's say with a thermocouple or just a thermometer or something. And they collected the data in a plate. So this could be like your pan, you have this little pan where we do waffles, pancakes and crepes, etc. So measure the temperature, this is what you get, okay? Now I took these data and I interpolated them to produce this kind of nice and smooth interface. This is not producing a new data, however, it's just finding a nice, smooth representation of the data. It's not improving the data that you have. The data that you have, that's the best you could do. That's what you have collected, okay? And with this, I will close the chapter on interpolation. We're going to switch back to Zoom now and chit chat about concerns, questions you have, and then you'll head off for the weekend, okay? All right, everyone, I am back. Okay. All right, with that, we finished our chapter on interpolation, okay? And we have a few minutes if you want to vent, complain about me, complain about the homework, ask questions, chat, say whatever is on your mind. You want to leave? Yes, Braden. Yeah. Oh, yeah. The midterms, they're all posted in the syllabus. March 4th is the first midterm. Please review your syllabus very carefully and the front page and all of those. Glad you asked that. I'm assuming review it will cover whatever we have covered before the exam. So as described in the syllabus, so it will likely also contain regression. It will contain regression because we will start regression next week. The homework 3. Yeah, we can post that. It's not going to give any code. The solution to the homework is not going to help you with homework 4 because we're not posting code. We post just the curves that you would get out of the code. And so typically I try to get this sometimes because problems change from year to year. It takes some time to can adjust the solution and put it back in our PDF and then post it. But typically those will be posted concurrently with the posting of the grade so that you have your 3 days to contest the grade. But Natalie, it's not, the posting of the solution does not contain code, so it's not going to help you with homework, with the coding for homework 4. Pardon me? Hmm. What do you mean? Last time from last year? Homework 3. Got it. Yeah, it's so we try, yeah, we try our best. Honestly, God bless my TAs. There, we got what, 66 homework assignments to grade, and so we try our best. And they're students like you are, right? So they are working and they're taking other classes, right? And so they have a heavy load. So we try to grade as fast as possible. But as homeworks, the linear system homeworks are the hardest. They take typically about a week to 2 weeks to grade. So there's going to be an overlap between the solution, but the assignments are not dependent on each other. The help sessions, however, should help you address sort of any concerns you might have had, like with your previous assignment, etc. And so, is anyone having the same concern and issue that Natalie is voicing? Oh, the feedback on the assignment. Okay. Yeah, and in previous installments of the course, I used to sit down and solve the homework in class. So you could see those actually from last year. I think some of them slipped through the radar and they're on YouTube. Um, but this year, I do not have time. And even with this online thing, there's just no time to process all of that because there's like 2 minutes here, 3 minutes there. So we will try to get you the homework assignment sooner, but unfortunately, it's just this is not because there's just gotta download all the codes and look at that and execute and run it. It just takes a little bit longer than what potentially other classes might have, who might have a smaller number of students and they have 2 TAs, etc. So guys, please read the syllabus. Please read the syllabus. I don't want to not answer your questions, but this is discussed clearly in the syllabus, and you can hold me accountable to that. There's no programming questions on the exams. The exams are purely similar to quizzes, especially now that we're doing everything online. They're going to be low stakes questions, a lot of them, a lot of low stakes questions that test your basic fundamental understanding. You might have to do a small derivation here and there that you will upload with your comments or in a separate file upload, but there will be no programming questions. Please read the syllabus. Go ahead. So I still don't understand the question. I think I saw that question. Do you want to ask it? Just ask me the question right now. Let's see. Yeah. So what do you think? That's my classic answer. Is what do you think? In the assignment, I do give you a hint, right? I do give you a hint to make sure that. Okay, so I'm opening assignment 4, iterative solvers. Okay. I'm actually going to stop the stream. Okay, if you end up using the routines that I have provided you with, make sure that you are taking as many iterations as needed to achieve the required tolerance. In other words, do not stop after a maximum number of iterations has been reached or passing a very large value of max iterers. So I'm going to ask you now the question again. Let's think about this. I want to make sure that you are stopping at a tolerance, not at a max iter. Okay. So one way to accomplish this is, yes. Yeah. So that you don't, so that in case, so let's suppose, you're trying to get to a tolerance of 0.5. And to get there, you need 500,000 iterations. But then you go and put in 100,000 or 1,000 iterations. Then you're not going to get to that tolerance. So what I'm saying is that first, I know this problem converges. It's not going to keep iterating for nothing because I gave you that routine, unless you messed up your coefficient matrix somehow. But it's just like an exact replica of what we did in class, right? So then make sure you put in a very large value for max iter because I know it's going to stop before max iter is hit. So that's your answer. Yeah. So do not stop. So in other words, do not stop after a maximum number of iterations has been reached. So it's maybe because English is my third language, so it might be that I have misrepresented that, but I try to be as accurate. I can see how this might have confused you, but the idea is don't make max iterations a condition. So either modify the routine to eliminate the max iteration condition, or just pass in a very large value for max iter. Okay. Thank you, Porter. Thank you. Okay. Okay. Mm-hmm. Well, cubic and quadratic are going to give you better interpolation. They're going to use some form of cubic or quadratic splines in 2D, something like that. And the point selection is complicated, is reserved to the algorithm itself. But if your data is, if linear interpolation gives you a smooth, nicely looking, thing you're happy with, pardon me, go with that. If not, try cubic or try quadratic, right? Sometimes, they are better accuracy to the point in between, but to the original data points, they all have the same accuracy because they have to pass through those original data points. Does that answer the question? Yeah. Thank you, Adriano. All right, everyone. I will see you next Tuesday. Bye.